Hello. Today we are moving to a new chapter in fluid mechanics, to chapter 5, where we will be talking about dimensional analysis and scaling. So let's put this chapter and what we're going to learn here in the context of what we have done so far in fluid mechanics. So in chapter 3 we talked about control volume analysis, macroscopic for macroscopic systems, and then we moved on to describe an infinitesimally small control volume, and we derived the Naiver Stokes equation. So we have the macroscopic view in chapter 3, the microscopic view, the differential view in chapter 4. And the last, so these are two very important tools to study fluid mechanics. And the last tool we are going to introduce in this course is dimensional analysis and scaling. And it's used a lot and frequently in analyzing experimental as well as computer simulation data. So let's talk about dimensional analysis and scaling and what we mean by that. So here is an example of what I just mentioned. So if I were to look at, to estimate the air friction, the air drag on this vehicle, in chapter 3 I would draw a control volume, and I would look at the momentum fluxes in and the momentum fluxes that leave my control volume, and do a momentum balance and mass balance, and from that I should get some estimate of the frictional force. So the analysis in chapter 4, we would write the Naiver Stokes equation for the system, define the boundaries. Here's one boundary, and the car surface will be another boundary, and write our boundary conditions, solve the Naiver Stokes equation, and implement the boundary conditions to evaluate the shear stress and pressure, and from that shear stress and pressure we can get the frictional forces on this vehicle. So that's all great. These are the two tools we have learned so far. And the third tool that we are interested in introducing in this section of this course is, one example of it is to do scale testing. So instead of doing a control volume analysis, or typically it's in addition to that, you would take a model of this car. So this car, you would get a toy model of this car, put it in a wind tunnel, and here you can see it's a scale model. It's not a real car relative to the size of the person, and you would subject it to a wind speed, and then in the wind tunnel you would be able to measure some friction on this car. And my question to you now is to think about, do you expect that the force that you compute or actually you evaluate in the wind tunnel on this toy car will be smaller, larger, or the same as the large car? Indeed, you have guessed right. It's going, we expect that it's going to be larger. So intuitively, we have some sense of scaling. But how much larger? Is it going to scale with the size, or is it going to scale with the size square, and why? And this is the knowledge we want to gain from this chapter, is how can we scale, how can we extrapolate the measurement we got in the small scale test to the actual size car. So that's what we call scaling up, scaling down. And we'll learn a lot of very useful real life fluid mechanics in this chapter. It's because it's things and stuff and information and knowledge that you can readily use to solve and analyze engineering problems. So this is a very useful chapter, and it requires a little bit of changing your thinking, as we will see in the next few slides. So moving on, what we want to do is, the first thing is we want to introduce the concept of scales, and then scales in general, and then we're going to infuse those scales into fluid mechanics, and we will see that they will give us something called dimensionless numbers, and we will see what those dimensionless numbers mean. And in fluid mechanics there are a few that are extremely important, and we will show some of those examples and try and solve some engineering problems in this respect. And we will have one of the take-home experiments on this particular chapter. All right, so let's talk about scales and what we mean by scales in general. So let's talk generally. You look at an ant and you look at an elephant, and I ask you, what is the size of an ant? What is the size of an elephant? You'll say, well, an ant is a few millimeters, maybe 1, 2, 3, 4, 5 millimeters, while an elephant is maybe 1, 2, 3, 4, 5 meters. So what here, we're looking at it very crudely. We're saying that the ant has no zeros in front of the millimeter, while an elephant has 3 zeros in front of the millimeter. So the ratio of size between an ant and an elephant is 1,000 times. And this sounds very trivial and very simple, but it has very profound physical implications. So let's look at two of those physical implications physical implications, which implies there are different behaviors exhibited by an ant and an elephant. And when we move on to look at fluid mechanics, where we look at systems of small scale and large scale, we will see that there are actually different properties of these fluid systems, primarily because of their scales and the disparity between their scales. So let's look at two implications where the size of an ant play an important role. So again, we're looking on the order of things. So we're saying an ant is on the order of a millimeter, so it could be 1, 2, 3, 4 millimeters, while an elephant is on the order of 1,000 millimeters. It could be 2,000, 3,000. We're using this term very loosely, of 1,000 millimeters. We're not saying 1 + 1 = 2. We're not doing that. We're just try to use things very crudely, but that will give us very deep insight. So let's look at the first aspect. It's easy for you to imagine an ant walking upside down in your ceiling, because you've seen it do that. But have you ever seen an elephant walk upside down on a ceiling? So we want to investigate this statement and this observation a little bit more deeply, as it connects to the scales and the sizes of an ant and an elephant. The other observation is, if you look at during the winter, ants actually hide during the winter time, and that also has an implication, we can argue that this is actually related to its size, and we will talk about it a little bit in a minute. So in the winter it gets a little bit cool, and we'll see how ants can respond to that change in temperature. But first, let's look at the argument as to why is it very strange for us to imagine an elephant walking upside down on the ceiling, while it's very easy for us to imagine that an ant can do that effortlessly? Well, primary effect is gravity, and so let's see what gravity, the weight of this creature, has to do with its ability to walk upside down. Gravity, or the weight, goes with the mass times g. So the gravity scales with the mass, and so what I mean scales, that is, if my mass goes up, the gravity or the weight of the object is going to go up. And the mass is just density times volume. So the mass scales with the volume. But the volume is some size, scales with the length cubed. So the weight of an ant scales with its length cubed, and the weight of an elephant scales with its length cubed. If an elephant is 1,000 times larger than an ant, how about its size? If you do, how about its volume, I mean? If you do the math, 1,000 cubed relative to 1 cube, so even though an elephant is 1,000 times larger than an ant, its volume is 1,000, so that's 1,000 million. An elephant is 1 billion times more massive, more voluminous than an ant. And in that lies the observation or the explanation why the effect of gravity on an elephant is much more pronounced than it is on an ant. So gravity on an ant is 1 billion times less important than it is on an elephant, and that explains why an ant can walk upside down on the ceiling. And now let's look at another aspect of this scale. The scaling argument. What we're arguing here, we're saying that scales now can decide or have implications on the behavior of a system. And we want to go in the next slides to talk about fluid systems, but here let's try and just show that this actually works in real life in a very large number of situations. So why do ants hide during the winter? We argue that that's because they feel cold, but why do they feel cold? So let's look at that a little bit closely. So how much heat does an ant store in its body? It's the heat capacity multiplied with its mass. So it scales how much it stores in terms of body heat, scales with the length cube. But how much heat does it lose? So it loses heat proportional to its surface area, and its surface area goes with its size squared. So now if I look at, and same thing for the elephant, its body heat storage goes with its length cubed, and its heat loss goes with its length squared. But now if I look at the ratio of the heat loss relative to the heat storage, how much heat is lost relative to how much heat is stored, it goes with 1 over L. So if I look at the loss to storage for an ant, it's 1, while for an elephant is 1 over 1,000. So an ant loses 1,000 times, the ratio of its heat loss to storage is 1,000 times larger than an elephant. It doesn't have that heat capacity to store, just because it has a small mass. It doesn't have that heat capacity to store body heat, so it can lose its heat extremely fast in the cold weather, and that can affect its survival. So for it to survive, it digs deep in the ground and hides down there. So you can see how, just by looking at the scaling argument, we were able to provide an explanation, an engineering explanation, physics-based explanation as to why this behavior occurs. Very good. So now I would like to give you another example, but I would like to invite someone else to give it for me. So, but let's look at that example first. So this is Mr. Galileo Galilei, and he was saying he lived in the 1500s and 1600s, and he was asking why are mammals as large as they are, and why is there a limit on their size? Why don't we see a mammal why don't we see an elephant that is 100 meters tall instead of 5 meters tall? So here is a group of mammals, and his argument 500 years ago was, well, since we now said that the weight scales with length scale, as the animal gets larger and larger, the weight becomes so huge that the bones will not be able to take it. So that's what we call a scaling argument, is that the size decides the behavior. And then came, so that's the argument of Galileo Galilei. He said, well, there's a limit on the size of mammals because they can't go beyond a certain size, otherwise their bones will break. So then came Professor Walter Lewin, retired professor at MIT, and he said, well, that's a very interesting argument that Galileo has come up with. So let's check it out. So what Professor Lewin has done is he actually went to a few mammals and tried to test them, see if this scaling argument is correct or incorrect. So you start with an argument and then you go do an experiment to see if this argument holds true. So this is Professor Walter Lewin, and here is the URL for the video.
I'm Walter Lewin. I will be your lecturer this term in physics. So whenever you make a measurement, you must know the uncertainty, otherwise it is meaningless. Galileo Galilei asked himself the question, why are mammals as large as they are and not much larger? He had a very clever reasoning, which I've never seen in print. But it comes down to the fact that he argued that if the mammal becomes too massive, that the bones will break. And he thought that that was a limiting factor. Even though I've never seen his reasoning in print, I will try to reconstruct it, what could have gone through his head. Here is a mammal. And this is one of the four legs of the mammal. And this mammal has a size S. And what I mean by that is a mouse is yay big and a cat is yay big. That's what I mean by size. Very crudely defined. The mass of the mammal is N. And this mammal has a thigh bone, which we call the femur, which is here. And the femur, of course, carries the body to a large extent. And let's assume that the femur has a length L and has a thickness D. Here is a femur. This is what a femur approximately looks like. So this would be the length of the femur. And this would be the thickness, D, and this would be the cross-sectional area, A. I'm now going to take you through what we call in physics a scaling argument. I would argue that the length of the femur must be proportional to the size of the animal. That's completely plausible. If an animal is 4 times larger than another, you would need 4 times longer legs. And that's all this is saying. It's very reasonable. It is also very reasonable that the mass of an animal is proportional to the 3rd power of the size, because that's related to its volume. And so if it's related to the third power of the size, it must also be proportional to the third power of the length of the femur, because of this relationship. Okay, that's one. Now comes the argument. Pressure on the femur is proportional to the weight of the animal divided by the cross-section A of the femur. That's what pressure is. And that is the mass of the animal, that's proportional to the mass of the animal divided by d squared. Because we want the area here. It's proportional to d squared. Now follow me closely. If the pressure is higher than a certain level, the bones will break. Therefore, for an animal not to break its bones, when the mass goes up by a certain factor, say a factor of 4, in order for the bones not to break, d squared must also go up by a factor of 4. That's a key argument in the scaling here. You really have to think that through carefully. Therefore, I would argue that the mass must be proportional to d squared. This is the breaking argument. Now compare these two. The mass is proportional to the length of the femur to the power 3 and to the thickness of the femur to the power 2. Therefore, the thickness of the femur to the power 2 must be proportional to the length L, and therefore the thickness of the femur must be proportional to L to the power 3/2. A very interesting result. What is this result telling you? It tells you that if I have two animals, and one is 10 times larger than the other, that S is 10 times larger. That the lengths of the legs are 10 times larger, but that the thickness of the femur is 30 times larger, because it is L to the power 3/2. If I were to compare a mouse with an elephant is about 100 times larger in size. So the length of the femur of the elephant would be 100 times larger than that of a mouse. But the thickness of the femur would have to be 1,000 times larger. And that may have convinced Galileo Galilei that that's the reason why the largest animals are as large as they are. Because clearly, if you increase the mass, there comes a time that the thickness of the bones is the same as the length of the bones. You're all made of bones, and that is biologically not feasible. And so there is a limit somewhere set by this scaling law. Well, I wanted to bring this to a test. After all, I brought my grandmother's statement to a test, so why not bring in Galileo Galilei's statement to a test? And so I went to Harvard, where they have a beautiful collection of femurs, and I asked them for the femur of a raccoon and a horse. A raccoon is this big. A horse is about 4 times bigger. So the length of the femur of a horse must be about 4 times the length of the raccoon. Close. So I was not surprised. Then I measured the thickness, and I said to myself, aha, if the length is 4 times higher, then the thickness has to be 8 times higher if this holds. And what I'm going to plot for you, you will see that shortly, is d divided by L versus L. And that, of course, must be proportional to L to the power 1/2. I bring 1L here. So if I compare the horse and I compare the raccoon, I would argue that the thickness divided by the length of the femur for the horse must be the square root of 4, twice as much as that of the raccoon. And so I was very anxious to plot that, and I did that, and I show you the result. Here is my first result. So we see there d over L. I explained to you why I prefer that to plot it. And here you see the length. You see here the raccoon, and you see the horse. And if you look carefully, then the d over L for the horse is only about 1.5 times larger than the raccoon. Well, I wasn't too disappointed. 1.5 is not 2, but it is in the right direction. The horse clearly has a larger value for d over L than the raccoon. I realized I needed more data. So I went back to Harvard. I said, look, I need a smaller animal, an opossum maybe a rat, maybe a mouse. And they said, okay. They gave me 3 more bones. They gave me an antelope, which is actually a little larger than the raccoon. And they gave me an opossum. And they gave me a mouse. Here is the bone of the antelope. Here is the one of the raccoon. Here is the one of the opossum. And now you won't believe this. This is so wonderful, so romantic. There is the mouse. Isn't that beautiful? Teeny weeny little mouse. It's only a teeny weeny little femur. And there it is. And I made the plot. I was very curious what that plot would look like. And here it is. I was shocked. I was really shocked. Because look, the horse is 50 times larger in size than the mouth. The difference in D over L is only a factor of 2. And I expected something more like a factor of 7. And so in D over L, where I expect a factor of 7, I only see a factor of 2. So I said to myself, oh my goodness, why didn't I ask them for an elephant? The real clincher would be the elephant, because if that goes way off scale, maybe we can still rescue the statement by Galileo Galilei. And so I went back, and they said, okay, we'll give you the femur of an elephant. They also gave me one of a moose, believe it or not. I think they wanted to get rid of me by that time, to be frank of you. And here is the femur of an elephant. And I measured it, the length and the thickness. And it is very heavy. It weighs a ton. I plotted it. I was full of expectation. I couldn't sleep all night. And there's the elephant. There is no evidence whatsoever that D over L is really larger for the elephant than for the mouth. These vertical bars indicate my uncertainty in measurements of thickness, and the horizontal scale, which is a logarithmic scale, the uncertainty of the length measurements is in the thickness of the red pen, so there's no need for me to indicate that any further. And here you have your measurements, in case you want to check them. And look again at the mouth and look at the elephant. The mouth has indeed only 1 centimeter length of the femur, and the elephant is indeed 100 times longer. So the first scaling argument that S is proportional to L, that is certainly what you expect, because an elephant is about 100 times larger in size. But when you go to D over L, you see it's all over. The D over L for the mouth is really not all that different from the elephant, and you would have expected that number to be with the square root of 100, so you expect it to be 10 times larger instead of about the same. I now want to discuss with you what we call in physics dimensional.
Okay, thanks to Professor Lewin. So here's the question. Did Professor Lewin rescue the argument of Galileo Galilei? So that's for you to answer. And let's move on. Next. All right, so that is about, we have talked about scales, and we've seen the example of the elephant and the ant, and we've seen the example of the bones of mammals. And now let's move on into fluid mechanics. So that's the idea behind scaling. And that same idea of scaling and scales, we'd expect it to also apply in fluid mechanics, because it's all about the physics of behavior. And so in fluid mechanics, there are actually 3 basic scales that we are interested in. we are interested in, or that we will see. Length scales, that's very obvious because that's what we've been talking about so far. There is velocity scales, just because we have flows and and liquids and gases are moving, and from those two we can derive a time scale. And each one of those length, time, and velocity scales has a physical meaning for a fluidic system, and they describe some property of that particular flow. But the idea behind scaling, just like we have seen it on length scales in the previous couple of examples. But in general, we're saying that as the system grows, the fluidic system grows larger and larger in size, we'd expect that a certain property or a certain force or power or energy will also scale in a certain way with the size of the system. And so we will be looking at ratios of scales between different systems. So let's talk about, show you some examples of scales in fluid mechanics. This is a wind tunnel picture of parachute testing. You'll see this is the scale of a human being, while this is the scale of the parachute. So they have different scales. Here there is jet engine testing or rocket engine testing in the desert. So there are multiple scales involved. There is the nozzle right here, which is, you can see, it's on the order of maybe tens of centimeters, and then you have the tens of centimeters or maybe a meter, and you have here the scale of the length of the jet itself, and it's on the order of kilometers, so it's around so here's a kilometer and a half, and then you have also the width of the jet itself. So this problem has different scales, as you can see. But these are the length scales of interest in this particular problem. Here's an example of length scales. You look at those two flying objects. Here's an insect and here's an aircraft. Let's just try and describe it before we look at it. The insect has a body, the aircraft has a body, it has a wing hanging on top, it has a wing hanging on top. So they look somehow similar, but if we were only to look at the pictures themselves without knowing much about their scales and what they are, without the context, we'll say, yeah, these are similar systems and we'd expect them to behave in a similar fashion. But once I tell you the fact that the length scale of this aircraft is on the order of tens of meters, maybe 10, 20 meters, 30 meters, so it's on the order of thousands of centimeters, while the insect is on the order of a centimeter, 1, 2, 3, 4, 5 centimeter in length, then that changes the whole picture on how I would expect these systems to behave from a fluid mechanics point of view. Insect flight is completely different than aircraft flight, just because of the difference in size between the systems. And this is what we have hopefully concluded from the previous examples. But these are the length scales we're looking at. And what length scale are we talking about? We might be referring to H being the length scale, being maybe the width of the body. Maybe it could be the wingspan for the insect. So you pick your. It's like we have looked at the jet in the previous, and the plume in the previous slide. A problem can have multiple scales, but in general we're talking crudely that this is on the order of centimeters and this is on the order of thousands of centimeters. And then the other thing that's of importance in fluid mechanics is velocity scales. So how fast does an airplane move? Does it fly? We'd expect maybe 300, 400, 500 kilometers per hour. So it's on the order of 100 meters per second. So that's a velocity scale. While if you look at an insect, it flies. If you see a fly zapping around in your room, it's moving maybe around on the order of a meter per second. So not only are the sizes, the length scales are different between those two systems, or those two apparently similar systems, but also the velocity scales are actually very large. So this is also 100 times larger in velocity. And for the jet that we've seen in the plume, maybe our velocity scale would be the speed of the flow coming out of the nozzle at the bottom. So length scales, velocity scales, and now that we have length scale and velocity scales, we can actually get a time scale. And what is a time scale for an aircraft like this? So if I take the length scale to be, let's say, the length of my object, and this aircraft is moving at a speed u, the time scale is the time for the object for the aircraft to moving at this speed to move one body length. So this is L, one body length from front to back. Then it'll take one time scale to move for its tail to move from here to here, and then another time scale L to move from here to here. So you get the idea. It's how much time does it take to clear the whole volume that it's occupying. And there are other examples that we can talk about and explain later. So these are the scales. But how do we apply scales to fluid mechanics? The basic equation that describes fluid mechanics is the Naiver Stokes equation. And the Naiver Stokes equation describes the force balance or Newton's second law for a fluidic systems. So let's try and combine those two concepts together, the concept of fluid mechanics and the concept of scales. The concept of fluid mechanics being the Naiver Stokes equation, and the scales being the velocity scale, length scale, as well as the time scale for the system. So somehow what we want to do is I want to take those scales and feed them into the Naiver Stokes equation. So how to do this? I want to infuse them in there and see what that, and fuse them together and what that fusion gives me. So let's come up with a way of doing that. So the way I would like to do this, in fact, now that I have, so let's look at one of those, the x component of the Naiver Stokes equation, and you'll see in the equation I have velocities u and v and w, and I also have time scale t, length scale x, or lengths x, y, and z. So you have velocities, and you have the dependent variables and the independent variables being the x, y, z, and time. And we also have the scales, the length scale. So what I would propose is I want to define a new x, I'm going to call it x star, and it's just the division of this x that I have in my Naiver Stokes equation by the length scale. So I'm sort of normalizing, so what I'm doing here is I'm normalizing my equation to normalizing the effect of the length scale of the particular problem. And same thing I will do with the y. I will define a y star to be, which is, a y star is a dimensionless number. It doesn't have units, it's normalized. It's just the dimensional y in meters divided by the length scale of the problem in meters. Same thing for the z star. And then I'm going to take them and plug them here into the x, y, the x. So we'll talk about that in a second. So that's for the x, y, and z, the independent variables. We have defined a new set of independent variables that are unitless, x star, y star, and z star. And let's do the same thing with the velocities u, v, and w. So I will define a unitless velocity u star, v star, w star, which is just my velocity u divided by my velocity scale. And we do this for all of them. For the U, V, and W. I get U star, V star, and W star. And now for the time, I will also define a unitless time, which is my dimensional time in seconds divided by my time scale. Time scale is just the L over U. So if I want to plug those up into the Naiver Stokes equation, let's see what that gives us. So here's my, since X star is X over L, right? I can take the L to the left-hand side, so my X becomes X star times L. So let me take this X and I will plug it here. Everywhere there's an X, I will plug it here and here and here and so on. And same thing for, so I'll plug for X to be X star times L. And same thing I will do for the Y and for the Z and for the U and the V and W. For the U, I'm going to substitute U star times U. And same thing with the V and the for the time t, I will substitute with t star L over U. So let's do this substitution. So for U, I've plugged in U times U star, and for the time I plugged in t star L over U. And I do it for the second term, the third term, and so on. And then I have my gravity and pressure terms. I'm just leaving them. I'm not so interested at the current time to deal with those, but we'll just leave them and assume that they get their proper way of being non-dimensionalized so that the equation is consistent in its units. Excuse me. And same thing you'll do for the viscous terms. And now you rearrange. So since the U and L are constants, we take them out of the derivative operator. So we factor them out. So we end up with the acceleration term, whether it's the convective acceleration or whether it's the local acceleration, both of them are going to give me a U squared over L as the factorial that comes out from this normalization, which is the process of infusing the scales into the Naiver Stokes equation. And then on the right-hand side, I have viscosity over density from the equation. That's over here. And I also get a U over L squared. So let me divide both sides by U squared to get rid of this and multiply it by L. So I'll have everything on one side. And that's what I get. So I get the same equation that we had here, but except with stars. So the velocities will have a star, and the times will have, and the times and x's and the lengths, the independent variables will have also a star. So the equation will look exactly the same. The x momentum equation now, this is the normalized x momentum equation, will look the same as the dimensional x momentum equation, except as we said with a star, plus what we have here, we have this extra term. So everything looks exactly the same. So this would be gravity star, and this would be pressure star, and here I have the Laplacian star of the velocity of the velocity vector, the dimensionless velocity vector. All right. Each term on the left-hand side, the accelerations have become unitless. So they became normalized. So they became independent, if you will, of the scale of the problem, whether it was 1 millimeter or 1 kilometer. Just because we've divided by that scale, the time scale and length scale, we have made everything dimensionless. But we still have, and we condensed all these units, all these dimensions, length scale and velocity scale in one item. So every term in this equation is unitless now. But now we have come up, we have, what this equation has thrown at us after the process of normalizing is this mu rho u, the viscosity mu divided by rho ul. And if you try and look at the units, the viscosity is Pascal second, and the rho is kilogram meters cubed, the velocity meter per second, and the length is meter. And if you look at it, it also has units of 1. So that's also a unitless or dimensionless number. And that is really what this whole exercise is about. When I take scales, as we have done here, and plug them, so let me just change the color of that. So I've taken the concept of scales, I've taken the concept of fluid mechanics, that is the Naiver Stokes equation, and now I have infused them together in the process that we have just described. That produced for me a dimensionless number. And we will see from now on that this dimensionless number is actually a very important quantity. So I would like you to pay attention to it and focus on this particular thing. So when we do this process, we get dimensionless number, and in fact, just because they are so important, they have names. So that thing, rho ul over mu, so the inverse of what we have in the equation, is called Reynolds number, and it's a very famous. Almost everyone who studies fluid mechanics will, at some point, have to invoke Reynolds number in their equation. So let's see what this Reynolds number actually means, and let's see what its implications on the equation are going to be. So that is really one. If that's Reynolds number rho u L over mu, that's actually this term over here is 1 over Reynolds number. And let's take now some asymptotic type of analysis where I go to limits of infinity and 0. What if my Reynolds number is infinite and is close to infinity? And what if my Reynolds number is close to 0? That means, let's look at an airplane. An airplane moves at 100 meters per second and its length scale is on the order of 10 meters. While I compare it to an insect, which moves only at 1 meter per second and its length scale is 0.01 meter. So you'll see that the Reynolds number for an airplane is thousands and tens of thousands of times, and maybe hundreds of thousands of times larger than what it is for an insect, airplane and an insect. So let's see. Now that we're talking about Reynolds number, that's what we mean. Reynolds number for an insect. So let's stick in an insect. So an insect moves at. So yeah, let's just, because that's sort of important. So for an insect, assuming both an insect and an airplane are moving in air, so the density and viscosity will be the same. An insect moves at let's say 1 centimeter per second, so that in meter per second 0.01. That's the length scale, it's around a centimeter, and it moves at around 1 meter per second. While an airplane, so I'm trying to look at the ratio between the Reynolds number between an airplane and an insect. So for an airplane, the airplane moves at 100 meters per second, we said, right? It's 100 multiplied by length scale. We also said it's on the order of tens of meters, so 10. So if I take the Reynolds number of an airplane divided by the Reynolds number of an insect, what do I get? What is the ratio? Here's 1,000 divided by 0.01. So I'm going to actually get the ratio of the Reynolds number is, that's the ratio, 1, 2, 3, 4, 5 zeros. So an airplane has a Reynolds number that's 100,000 times larger than an insect. Great, so let's move on to the next slide, where an airplane has a very large Reynolds number while an insect has a very small Reynolds number. So if I stick with a very large Reynolds number, so we're talking about an airplane. So let's see what that's our equation. Here's our acceleration, dimensional, normalized, dimensionless, normalized, my pressure term, as well as my viscous term, normalized. And then here's my 1 over RE. That's the Naiver Stokes equation after normalization. If I put Reynolds number to be very large, what is that? Let's say put it infinity. So all that term goes away. So all this term just disappears from the equation just by saying it's a large system. And I end up with my potential flow theory. So viscous forces, which are in this viscous term, so this was the acceleration term, pressure term, and here is the viscous term. The viscous forces, the friction, viscous friction is negligible on large airplanes. That's very interesting. And that's the foundation of the potential flow theory, the basic theory that describes aerodynamics and aerodynamic shapes. And it comes from this basic scaling argument that Reynolds number for airplanes is very large, so the viscous effects compared to the acceleration effects or inertial effects is minimal, so we can actually not even look at it. We can erase it from the equation. So all this part of the equation we don't study in the potential flow theory. We only look at the pressure term and we look at the acceleration term. Now let's take the extreme case where I'm looking at insects, where the Reynolds number is extremely small. And when it's extremely small, this number becomes very important. And in fact, the acceleration term, the inertial term we call it, compared to the viscous term becomes very important. So the acceleration term becomes very negligible. So we can actually get rid of this. So my equation boils down to, this is 0. So this is my equation. So we have the pressure forces and the viscous forces. And this is another theory that describes flows that are creeping. And one important is the Stokes flow, which we will probably look at very briefly in one of the drag coefficient plots later on. So when we infused the concept of scales into the Naiver Stokes equation, it gave us a result which is dimensionless numbers. And we found out that those dimensionless numbers actually have a very profound physical meaning, and they can tell us right from the beginning, if I'm dealing with a large system, I don't really need to worry about the inertial term. But if I'm dealing with a very small, with the viscous term. But if I'm dealing with a very small system, which has a very small Reynolds number, I don't really need to worry about the inertial term. So this is the dimensionless numbers, like the Reynolds number, are very powerful tools to study fluid systems. Now let's look at the Reynolds number, what it means. Okay, there's a slide missing. So we could look at the Reynolds number to be, so it could, we could look at it to be as the ratio of length. So this is Reynolds number, rho u L over mu. And if I just keep this length on top and take the rho u to the bottom, so divide by viscosity, just it's the same equation, the same quantity, but I rearranged it. So that's a length, because Reynolds number has units of 1, it's unitless. And here I have units of length. This must mean that this is also units of length. And that's, remember when we talked about the length scale, it's the distance it's moved by the object at that certain speed in that certain time unit. So it's a length scale of the body. So this we call it inertial length scale. And this, because it has viscosity, this also has units of meter. This whole term in circle has units of meter, but because it has viscosity, we call it the viscous length scale. So that's one way of looking at Reynolds number. We don't really have a strong feel of what we mean by inertial length scale and viscous length scale, but we will have some experiments later on to do to understand this concept of scales, viscous and inertial scales. But I can look at the Reynolds number in a different way. I could say, well, my Reynolds number is rho u over L. Last time I moved the rho u to the bottom. Now let me just move the rho L to the bottom. So I end up with velocity ratio, velocity over velocity. So first we looked at the Reynolds number as length over length. Here we're looking at it as a velocity, inertial velocity over a viscous velocity. So here it's a velocity scale, sorry, not length scale, velocity scale. And thirdly, we can look at the Reynolds number as time scales. So rho u L, if I want to make this as time, I will get L over u here, so that's time. And then those, I will move them to the bottom and add another u, so over rho u squared. Right? Exactly, over rho u squared. So L has units of meter, velocity has units of meter per second, so we're dividing by meter second minus 1. So the meter goes with the meter, and the second one minus 1 becomes second. So that has units of time over time. So that's an inertial time scale. It's the time it takes for the body to move one body length at that particular speed. That's an inertial time scale. And here at the bottom, I have a viscous time scale. So that viscous time scale is just the product of dividing mu over rho u squared. So it's a time scale ratio. All right. So we will stop at this point, and we will take it over from here on Tuesday. I have a few more things to say about Reynolds number, but we'll leave that for next Tuesday. Thank you for listening, and see you next time.